Dr. John Mather is NASA's Nobel Prize-winning scientist, and he's also the senior project scientist on the James Webb Space Telescope. So Dr. Mather, tell me from your perspective on the James Webb Space Telescope, how excited are you about this mission and why?
It is the most exciting thing I could possibly imagine to be working on. It is the successor for the Hubble Space Telescope, and it will be far more powerful and much larger and be able to see things the Hubble could never see.
Is that right?
Today I wanted to tell the story of why are we building our telescope the way that we're building it, because basically people, although they don't quite say so, they think your telescope looks weird. So our telescope does look different from every other telescope you've ever seen. It doesn't look like Galileo's little tube with a lens at each end. It's way different from anything that we've ever built for anywhere before. So I wanted to tell you a little bit about the story of why it looks like it does. I am the senior project scientist, which means I'm older. And it also means I'm the only person still working on the project who was here on the first day, which was in October of '95. And what I really hope is that we'll get a big surprise out of our new observatory, because that's always happened every time we built a new great observatory. Something that nobody ever guessed was out there would happen. It's a reminder that our imagination, no matter how feverish we might feel, is still limited, and we don't usually guess what nature has done. What I love, though, is the surprise that once in a while we get. So, as an example, when we built the Hubble Space Telescope, people were sure they'd be able to see the first galaxies being born out of the primordial stuff. And the first thing they found out was, no, you can't. They're too faint, they're too far away, and they're too red. And I got a phone call that it's time to start the study of the new telescope. So the Hubble telescope had been repaired. We could see that it was brilliant and powerful, but it still couldn't show us everything. So what are we going to do next? A committee was formed, of course, and they wrote a little book, and they said, build the new telescope like this. It should be an infrared telescope. It should be at least 4 meters in diameter, which is considerably bigger than the Hubble. And we've ended up building one that is 6.5 meters in diameter, more than twice as big as Hubble, and very powerful. We had to invent 10 major inventions in order to make this telescope happen. We had to invent ultra-lightweight mirrors that could be cooled down to very low temperatures in outer space. So even though our telescope has 7 times the collecting area of Hubble, its mass is only half as much. So that's a truly incredible accomplishment. Those big mirrors, they are so light that you could easily lift one of those 18 segments yourself. We won't let you, but you could, because the metal has been cut down to 2 millimeters thick. And nevertheless, it's polished to the same accuracy almost as the Hubble telescope has. So beryllium's an interesting material. Beryllium comes in nature as hexagonal crystals. Well, that's not good. It's not going to keep its shape when it cools down. So metallurgists have spent a fortune and a long time making beryllium into a perfect material. Make powder, compress it into a vacuum in a furnace, and make a block that's totally uniform. And it doesn't warp when it cools down. That's amazing. When you see the mirror, you'll see that it's gold-coated. Well, it's gold-coated because that's the best reflector for infrared light. And it takes about an ounce to cover this huge thing. It is a joint project of NASA along with the European and Canadian space agencies. It's an enormous project. It's the most difficult one we've tried at NASA in science and engineering for science. So we're building a telescope that could see a bumblebee at the distance of the moon, just from the heat that the bumblebee gives off. It is named for the man who went to President Kennedy with a plan for the Apollo program. Pretty clearly, we test what we can, and when a thing cannot be tested exactly as it will be operated in flight, then we must demonstrate to good satisfaction that we've done everything that we could do. So, for instance, we know that we can't deploy the full-scale sunshield for the James Webb Telescope in zero gravity and the right temperature. It's about as big as a tennis court. It's made 5 layers, so the heat from the sun is mostly reflected off the first layer. What's not reflected is transmitted or emitted through. Most of that is intercepted by the next layer and goes out through the gap between them out to the side. And you do this with 5 layers, and eventually less than 1/1,000,000th of the original sunshine heat gets through to the back. So what we have to do is to analyze what we can to test subscale versions, test them every possible way that we can test them so that we develop the experience. There are a few things where you just have to say, I can't possibly test it exactly the right way, but I have to test every feature of it in some way so that we can be sure that we didn't just, forget something. So today we are riding on an immense wave of discovery. Incredibly powerful human society that we're part of is now able to do practically anything at once. It takes a little while, but we get there. We are putting in huge efforts in every area of science and engineering. We are really only held back by our imagination and the laws of nature. We do risky things because it's the only way to get at the answers that we're after. You can't say, I don't really want to know, because we do really want to know. But the only way to get at the answer is to build this kind of equipment. We had to perfect 2 different kinds of infrared detectors. We had to learn how to make amplifiers to work with these low temperature detectors. We had to learn how to get one of the detectors down to 7 degrees Kelvin. It has to be folded up really small so when we get it up there it can unfold properly in outer space. We have to rehearse and practice and we have to find those little mistakes that people always make and fix them. So it's difficult, but it's worth it. In order to discover the things that we have never seen before, we need the best equipment we can possibly have. So the telescope that we're building has no substitute. There's no other way to get at this scientific discoveries that it'll make. What it'll really find that we don't know? Well, I don't know. It's a mystery. So we build these telescopes with great confidence that we will open up new mysteries of the universe whenever we build them. It's happened time after time after time for centuries. To tell you the truth, I don't really have much in the way of theories, but a lot of other people do. So I'm pretty much in the business of let's collect some evidence and take some pictures and make some measurements. And then other people tend to figure out the theories that explain them. So it's not completely stupid and well, anyway, it's pretty ambitious. It's just really difficult. You know, when you look out and see what is the world like, it is astonishing in every way. Every little thing is so special and different, and yet there are some universal principles that seem to organize it, and we don't know how they work. As just an example of the awesome questions that are in front of us. Another thing we don't know is where did the chemical elements come from? We know from pretty good observations that the early universe had only hydrogen and helium in it. So, but we're not made of that mostly. We're made of other chemical elements. We do pretty much know that they came from stars that burned the hydrogen and helium and blew up and left the material out into space again. So we know that we're recycled from those materials, but the details of how it works are still pretty unknown. So we know about the expanding universe, which we call the Big Bang. It was very hot, very compressed. Somehow that turned into us. How did that happen? We know that stars and galaxies formed somehow, billions of years ago. We know that they're still being born today, not too far away. We'd like to know how planets become habitable. How do they come out to be just the right size and temperature to have just the right amount of water and oceans and continents so that they could be like Earth? All of these things are huge questions for humanity. And I think everybody wants to know where did we come from, and I especially do, because it's like the most difficult and interesting challenge in science. So we have the story of the expanding universe. That's pretty sure. What's unsure is what was there in the earliest moments. Because we know if you try to take the laws of nature that we've heard about so far and discovered and tested, and you imagine what are they like when the conditions are so incredible, you can't imagine they really are right anymore. So we're got to guess. A lot of guessing going on about those first moments. One of the cool things about the infrared range, though, is that we can also see the most distant universe, because as the universe is expanding, the light that we're receiving from the most distant parts of the universe expands also. So when it starts out as visible light, but when we get it, it's infrared. So that's why we've decided to make a telescope that's special for infrared radiation. We watch a star for a long, long time. Once in a while, a planet orbiting that star will block some of the starlight. It'll go between us. So some of the starlight will go through the atmosphere of the planet on the way to our telescope. It means that the planet looks bigger at some wavelengths than at others. It's not just an opaque disk. So that means then we can figure this out, and we can detect the characteristic signatures at certain wavelengths of some molecules in the atmospheres of other planets. So we proved we can do things when we have the support of the people and the right mindset. We did, and we still do.
And how do you provide mission assurance once it's in orbit or once it's in space?
It's very tricky to deploy this thing, but we rehearse everything in advance.
Okay.
Many times here on the ground, we deploy and fold again. Then in space, we know what we're going to do. Much of the detail has already been worked out, day by day, hour by hour, minute by minute, what we're going to do when we get there. We have telemetry, which is instrumentation on board that tells us whether things have been done correctly. And we have a plan for what happens just in case. So for instance, we have on everything that's supposed to move, we have 2 ways to make it move. A motor has 2 sets of windings and 2 sets of electronics to control it. So one doesn't work, we try the other one. That's one of the ways that we know it should work, but we will certainly be watching it very carefully and thinking about it as it goes.
Awesome.
So this makes it, in a way, less hazardous than the Mars lander, which had to do it all by itself.
Absolutely.
We get to watch the step-by-step process and then to intervene if something's not quite right. And we have our backup plan. So how long before we get pictures? It takes a total of about 2 weeks to get it unfolded, a total of 6 months to get it all set up and working. And then you should expect beautiful pictures. So I promise you will not be disappointed.